All right, now this is a tough one here. This is the Boltzmann distribution, okay? And I need to say a few words, and you have one problem that deals with that, and it's really useful in biochemistry also, because it kind of tells you when you have molecules that can be in different states, you know, what state are they most likely in, and that really depends on the difference in energy between states. But to introduce you to that, you all have learned about one thing in Gen Chem, and that's this. What I'm going to circle right here is that when we have electrons have different energy levels, right? These energy levels are, we said the energy is quantized, right? We have different states and different orbitals, okay? So this may be the ground state right here, and then the first excited state, and then the second, and so on. And the molecules would rather stay in the lowest energy state, but if you give them thermal energy, okay, or if you give electrons thermal energy, if you, let's say, put a lot of electrical current in a gas, then electrons might be able to jump to a higher energy level. This is where you have absorption of light and so on. And if you give it even more energy, they might move to higher and higher level. The same thing happens actually for vibration. Vibrational motion can occur with different levels of energy. The higher the temperature of the object, the higher the vibrational energy. The same thing for rotation. Okay. Now the only difference between these different modes is the actual difference between the energy levels. Okay. Now for those of you who've had Chem 4616, this is really what Troya talks about, I'm sure, a lot about, is the energy level, the difference in energy levels between vibrational state, between electronic state, between rotational state, and why the state here, it looks like there's a continuum. The states are very, very, very close to each other. Okay, there's very little difference. So we don't even talk about quantization very much if we have a big box like we have in real life for gases, for example. But the key thing is molecules and electrons and so on can occupy different states, and these different states have different energy levels. And what we'd like to know is, well, if we have, let's say, 1 mole of electrons, are all the electrons in the lowest energy state, or are they in higher energy state? But that depends actually on the temperature, okay? And there's an equation called the Boltzmann distribution that relates, and this is this equation that is shown right here, that relates the number of species, let's say number of species N2, in the energy level E2. So you can think of this is E1, this is E2, and you can apply this to any level, okay? So N2 corresponds to E2, and we have N1 particles or electrons or whatever in energy level E1. And the ratio of N2 over N1 is simply E to the minus E2 minus E1 divided by KT. Now, KT, K, is what we call the Boltzmann constant. If we're talking about the energy of an electron or energy of a vibration or of a molecule, we're going to be using the Boltzmann constant. If we talk about a mole of anything, a mole of electrons or a mole of molecule, then we will use the gas constant. The only difference between R and K is simply that when we talk about K, we talk about a single particle, a single mole, a single bond, a single unit. When we talk about R, when we use R, we refer to a mole of something, okay? So K and R are related by Avogadro's number. K is actually R divided by Avogadro's number. K is a very small quantity, obviously, since it's for one molecule, okay? So K times T is the thermal energy of one molecule in the same way that RT was the thermal energy of a mole of molecule. Conceptually, what does it mean? It means that if, let's say, you have a very large difference between the two energy levels, okay? So if E2 minus E1 is very large, okay, and positive, E2 is much greater than E1. What is the consequence? So you look at the equation, then E2 minus E1 is very large compared to KT. So that number in the exponential, in the argument of the exponential, if E2 is much, much more than E1, that number is large. right? So when E2 minus E1 is large compared to KT, then this exponential becomes 0, N2 is 0, okay? So if E2 is very high, so if you have a very high energy level, okay, compared to E1, so this is E2 over here, and this is E1 over here, and we are at low temperature, then KT is small, E2 minus E1 is large, this whole number is large, N2 is 0, and N1 is large, right? N2 is 0. All the molecules at low temperature would be here. Now, if I make the temperature very high, KT is very high, then I populate equally all these states. Okay, this is what the Boltzmann equation is about. We're going to talk about this in a context of population of states, let's say for conformational states in a peptide or in a protein. Let's assume a polypeptide has two different states, two different conformations. Okay. Conformation A, conformation B. And conformation A, for example, has a higher energy than conformation B by a difference which is 7.5 kilojoules per mole. So now we're dealing with moles, okay? So that means in my Boltzmann equation, I'm going to be using the gas constant, not the Boltzmann constant. All right, so all I have to do is plug in this equation EA minus EB, that's 7.5, okay? And because EA is more than EB, EA minus EB is positive. So we have E to the minus 7,500, okay, in joules per mole. And I have to transform kilojoules to joules because R is 8.3145 in joules per Kelvin per mole. So make sure you work out the units here, otherwise you will have problems with that homework assignment. And then your temperature, and you divide everything out, and you get 0.054. So that tells you that, okay, if we have two conformations, A and B, and A is higher in energy than B by 7,500 joules per mole, then we're going to have 0.05 A for 1B, which means we have about 20 times more chance to find the molecule in conformation B than in conformation A. Now, when I gave you a homework assignment, and I'm asking you to use this equation, what I wanted in the assignment actually is I'm going to want the mole fraction of molecules in state A and state B. So what I want is found the mole fraction of molecules in state A, Na over Na plus Nb. So I don't want simply the ratio Na over Nb, I want the mole fraction.